Let's take the same settings as before. So we have an index set I, which is a subset of the real values. We have a real valued stochastic process. Then this real valued stochastic process is called a Markovian Gaussian process if it is a Gaussian process that also fulfills the Markov property. And the Markov property is basically just saying that the evolution of your Markov process in the future will only depend on your present state and not on the past history. Or, in more mathematical terms, if the conditional probability distribution of any future state of this process, and we take it conditionally on the present and the past states, will only depend on the present state. So the conditional probability of any future state given any value for now and in the past is only dependent, is exactly the same as the probability, the conditional probability distribution of this future state given the situation that we are in now. So any future state of this process will only depend on the current position, the current value, and not on what happened in the past. To generate such a process, we will use the property that any conditional probability of a multivariate normal distribution is also following a normal distribution. Let us denote for simplicity x of ti as x of I. The same for mu of ti will be mu of I, and sigma ij will correspond to my variance-covariance function, so k of ti tj. If we then look at the vector xi plus 1, we know that because it is a Gaussian process, this vector will follow a bivariate normal distribution. Bivariate normal distribution with mean mu I plus 1 and the following variance-covariance matrix. In this case, we know, because of the properties we saw in chapter 4, that the conditional probability of xi plus 1 given xi will also follow a normal distribution. If we then take the formula from the 4th chapter, we can also determine the parameters of this normal distribution. If we look back at this formula, we can identify the different parts. So xp in our case will be xi plus 1, xq is xi. This means that p is equal to 1, so it will be a univariate normal distribution. Since xq is xi, it means that mu q is mu I, and mu p will be mu I plus 1. And then if we make the split of the variance-covariance matrix, we see that sigma p corresponds to sigma I plus 1, sigma q corresponds to sigma I, and sigma r corresponds to the covariance sigma I plus 1. As such, the mean of our univariate normal distribution will be mu I plus 1 plus sigma I plus 1 over sigma I times x minus mu I. And then the second parameter, we replace sigma p, sigma r, and sigma q with their respective variances or covariances. So we get sigma I plus 1 minus sigma squared I plus 1 over sigma I. Using this information, it is then possible to generate values from a Markovian Gaussian process. For given expectation function mu and a covariance function k, and for chosen time points t1 to tn, we can generate a Markovian Gaussian process by the following algorithm. As you can see, because of the fact that we will be using those conditional distributions, it will be an iterative process. So we start with the first time point t1. We construct or we calculate the mean at t1 and the sigma 1, so the variance at t1. We draw an observation from a standard normal univariate distribution, and then x1 will be mu1 plus the root of sigma 1, so the standard deviation times this value for z. You see that in the first step we just use a normal distribution without any condition on previous states, because we are still at the first time point. There is no past that we can use to find the distribution of this point. And then step by step we move on until we reach time point tn. So in each of those steps we calculate the mean using the mean function, and we calculate the variance and the covariance. So we calculate the variance for xi plus 1. So this is the variance for our stochastic process at time point ti plus 1. And we also calculate the covariances, so the covariance between xi plus 1 and xi, so basically between the observations or the values in ti and ti plus 1. Then we again make a draw from a univariate normal distribution, and then we use the conditional probability that we calculated on the previous slide. So we will know that for this observation we can transform this standard normal distribution, or this value from the standard normal distribution, to the normal distribution, the conditional normal distribution that we calculated previously. The way we do this is, again, we take xi plus 1 is the mean plus the standard deviation times z. And then in the end we just return the sequence x1 up to xn.